Hey everyone, and welcome. Today we're going to tackle two of the absolute cornerstones of modern math, relations and functions. We're going to break them down, see how they're connected, and really get a feel for the rules that make them so incredibly powerful. So, let's just dive right in.
So, let's kick things off with a pretty big question. How do we even describe connections using math? Think about the links between people on social media, or how numbers can be less than each other, or even just how a price is connected to an item in a store. Well, math gives us a really precise language to talk about all of these relationships. And that language, it all starts with something called a relation.
So let's start with the first most fundamental concept. I want you to think of a relation as the Wild West of connections. Seriously, it's this super broad, super flexible idea that lets us link things from different groups in pretty much any way we want. There are not a lot of rules out here.
Okay, now for the formal definition. I know it sounds a little complex, but let's just break it down. Imagine you've got a set of shirts, set A, and a set of pants, set B. The Cartesian product is just every single possible outfit you could possibly make. A relation is just any handful of those outfits that you decide to pick out. That's really all it is, just a specific collection of ordered pairs. Now, every relation has three key parts you gotta know. The domain is your set of starting points, your inputs. The codomain is the entire universe of possible destinations you could go to. And the range? That's the set of destinations you actually ended up visiting. Here's an easy way to think about it. The codomain is the full menu at a restaurant, but the range is just the food you actually ordered. Okay, so as we said, relations can be a bit chaotic, a total free-for-all. To make them really useful, we need to apply some rules to, well, tame that chaos. These rules give our connections some really meaningful and predictable properties. Let's see how that works. Our very first rule is called reflexivity. This one is all about self-connection, and it's a really foundational check for any relation. So, a relation is reflexive if every single element in your starting set is related to itself. Just think of it like this. In a reflexive world, everyone is connected to themselves. It's a basic check for self-identity within the group. And here's the test. It's super straightforward. To be reflexive, if your set has the numbers 1, 2, 3, then your relation absolutely must include the pairs 1, 1, 2, 2, and 3, 3. It can have other pairs, sure, like 1, 2, but those self-pairing connections, they are totally non-negotiable. All right, next up, we have symmetry. This rule is all about making sure our connections are two-way streets. The rule for symmetry is as simple as it sounds. It has to be a two-way street. If there's a connection going from A to B, then there absolutely must be a connection going from B right back to A. If one exists without the other, nope, the relation is not symmetric. So when you're checking your list of pairs for symmetry, if you see a 1, 2, you have to immediately look for its partner 2, 1. If it's there, awesome, you keep checking. But if it's missing, you can stop right then and there. You've already proven the relation isn't symmetric. And our third and final big rule is transitivity. You can think of this as the friend of a friend property. A transitive relation creates this kind of logical chain. If there's a path from A to B, and then another path from that same B onward to C, a transitive relation guarantees that there's also a direct shortcut from A straight to C.
So when you're checking for this one, you're hunting for those chains. You spot a 1, 2. Then you spot a 2, 3. See how that 2 in the middle connects them? Well, for the relation to be transitive, that shortcut pair, 1, 3, must also be in your set. If it's not, the chain is broken. Now, what happens when a relation actually follows all three of these rules, reflexive, symmetric, and transitive? Well, we get something really special. We get a true all-star in the world of mathematics. It's called an equivalence relation. And this is the gold standard, for real. A relation that has all three properties is so powerful because it does something incredible. It groups elements that are equivalent, or the same, in some important way. It neatly sorts a whole messy set into meaningful, separate categories. This table right here is your ultimate cheat sheet for checking. You just run down the list. First are all the self-pairs like A, A there. That's your reflexive check. Next, for every pair you find, is its mirror image also in the list? That's your symmetric check. And finally, does that chain rule hold for all the connections? That's your transitive check. If you get 3 yeses, congratulations, you've found an equivalence relation. Okay, so we've managed to tame the Wild West of relations. Now we're going to cross a pretty big divide into a world with much, much stricter rules.
We are moving from the anything-goes flexibility of relations to the absolute precision of functions.
So what is this great divide? Just look at this comparison. A relation is like a chaotic bulletin board. You can pin a string from any input to as many outputs as you want or none at all. But a function? Oh, a function is a predictable machine. You put an input in, and you are guaranteed to get exactly one output. Not 0, not 2, exactly 1 every single time.
This quote really nails the relationship between the two. A function is just a special, much more disciplined kind of relation. Yeah, it's still a collection of pairs, but it has to obey that one strict rule. Every single input is used, and it's used exactly once. A lot of relations just don't follow that rule, and that's why they don't get to be called functions.
But even within this world of precise machines, there are different models. We can fine-tune our functions to have even more specific and really useful properties.
And this table gives us a fantastic summary. A 1-1 function means that no two different inputs will ever point to the same output. It's a perfect pairing. An onto function guarantees that every possible output is actually used at least once. Remember our menu analogy? Nothing is left unordered. And then there's the most powerful of them all, a bijective function. It's both 1-1 and onto, creating a perfect one-to-one correspondence between two sets. This is the absolute peak of precision. You know, this idea of a bijective function, this perfect mapping that is also perfectly reversible, it's way more than just abstract math. It's essentially the blueprint for a perfect code. And that leads me to a final thought for you to ponder. Where in our modern world, from secure online communication to compressing huge data files, do we completely rely on these kinds of perfect, reversible codes just to make everything work?